73 seconds. That's it. That was the entire final flight of the Space Shuttle Challenger. Millions of people were watching it live, and then suddenly the sky was filled with this huge white fireball. I mean, imagine watching that without knowing what had happened. One moment, everything looks fine. The shuttle is climbing into the sky, and a few seconds later, it's just gone. Most people believe Challenger had simply exploded, but, well, that's not exactly what happened. The real failure began inside one of the rocket's boosters, in a gap only a few millimeters wide. And here's the part that makes this story so frustrating. Engineers had already warned that the cold weather could make this exact part dangerous. They knew something wasn't right. But Challenger launched anyway. So how does a small rubber ring bring down one of the most advanced machines ever built? And maybe even more importantly, how does a serious warning get lost before a launch like this? This is Failure Atlas, and this is the story of Space Shuttle Challenger. Okay, so it's January 28, 1986. Challenger is sitting on the launch pad in Florida. There are 7 people on board, 6 astronauts and a school teacher named Krista McAuliffe. Krista is supposed to become the first American teacher in space, and this is a really big deal, you know? She plans to give lessons from orbit. So teachers, parents, and school children all across the country are watching the launch live. Just think about that for a second. Children are sitting in classrooms, watching their teacher prepare to fly into space. This isn't supposed to be a dark day. It's supposed to inspire an entire generation. But that morning, Florida is unusually cold. Really cold. There's ice hanging from parts of the launch tower. The temperature near the ground is only 36 degrees Fahrenheit, or about 2 degrees Celsius. That's 15 degrees colder than any previous shuttle launch. And deep inside the right rocket booster, that cold is changing the behavior of one very important piece of rubber. Now, before we go any further, I need to quickly show you how this thing worked. Don't worry, it's actually pretty simple. You know those 2 long wide rockets attached to the sides of the shuttle? Those are called solid rocket boosters. And during launch, they provide most of the force that lifts the shuttle away from Earth. These things are unbelievably powerful, but they're also huge, way too large to build and transport as one complete piece. So each booster is made from several steel sections. Think of them like giant metal cans stacked on top of each other. And of course, every place where 2 sections connect has to be sealed, because inside that rocket is burning fuel, creating extremely hot gas under enormous pressure. If that gas finds even a small path through a joint, yeah, that's very bad. It can start burning straight through the side of the rocket. So engineers used 2 rubber circles inside every joint. They're called O-rings. Basically, when the booster ignites, these rubber rings are supposed to press against the metal and stop the hot gas from escaping. Simple enough, right? Well, there was one problem. At ignition, the enormous pressure inside the booster made its metal walls bend slightly. Not by much. You wouldn't even notice it by looking at the rocket. But the movement opened a tiny gap inside the joint. The O-ring had to spring into that gap almost instantly and seal it. Warm rubber could do that quickly. Cold rubber was slower. It was like taking a rubber band from a warm room and comparing it with one that had been sitting in a freezer. The cold one feels harder. It doesn't return to its shape as quickly, and inside this booster, a tiny delay was enough for burning gas to get through. Now, you might think nobody knew this could happen, but that's what makes the story worse. The warning signs were already there. After earlier shuttle flights, engineers had found damage on some of the O-rings. Hot gas had burned away parts of the rubber. In some cases, Black Suit had even traveled past the first seal. And honestly, that should have scared everyone. But the boosters had never completely failed. Every shuttle had still made it home, so little by little, the damage started to feel normal. Not safe, just normal. And there's a huge difference between those two things. It's like driving a car with a warning light on the dashboard. At first, you see the light and think, oh no, something wrong, right? But then you drive to work and nothing happens. The next day, the car still works. After a few weeks, you barely notice the light anymore. The problem hasn't disappeared. You've just become comfortable living with it. And that's exactly how dangerous problems slowly become accepted. So now we get to the night before launch. Engineers working for Morton Thiokol look at the weather forecast. Morton Thiokol is the company that built the rocket boosters, and its engineers are worried. They have never launched these O-rings in temperatures anywhere near this low. Their coldest previous experience was around 53 degrees Fahrenheit or 12 degrees Celsius. But for Challenger, they believe the O-ring joint could fall to somewhere around 26 to 29 degrees Fahrenheit. So below freezing. So the engineers say we should not launch in these conditions. A long telephone meeting begins between Thiokol and NASA. And this is where things get messy. The engineers try to explain the danger using information from earlier flights. They can show that cold makes the rubber slower. They can show that O-rings have already been damaged. They can also show that this launch is far outside their previous experience, but they can't point to one exact temperature and say, here, at this number the joint will definitely fail. Because, well, they have never tested a real launch in conditions this cold. And real life doesn't always give you a clean line between safe and deadly. Sometimes all you have is a warning that everything is moving in the wrong direction. NASA managers ask for stronger proof that the launch will be dangerous. Thiokol's managers stop the call and discuss the situation privately, and when they return, they have changed their recommendation. The company now supports the launch. Some of the engineers still disagree, but their concerns don't reach everyone making the final decision. In fact, the later investigation found that some senior decision makers didn't even know Thiokol had first recommended against launching. I mean, how can you make the right decision if you don't even receive the strongest warning? But that's what happened. Challenger was cleared for flight. The next morning at 11:38, the engines ignite. For everyone watching, the launch looks completely normal. Challenger slowly rises from the pad and then climbs into the sky, but less than 1 second after ignition, cameras record puffs of black smoke coming from the joint in the right rocket booster. The hot gas is already damaging the O-rings. Then the smoke stops, and for a while everything still looks fine. Material from the burning fuel may have temporarily blocked the damaged area, kind of like dirt being pushed into a leaking hole. But the joint hasn't repaired itself. The temporary blockage is weak. So as Challenger flies higher, it passes through strong winds. The shuttle's control system moves the boosters slightly to keep the vehicle on course, and those forces disturb the damaged joint. Around 58 seconds after launch, a flame appears on the side of the right booster. At first it's small, then it grows. The flame starts burning into the shuttle's huge external fuel tank. But the crew doesn't receive a clear warning about what is happening outside. Challenger keeps climbing. 68 seconds, 69, 70, and then at 73 seconds, the damaged booster pulls against the weakened fuel tank. The tank breaks apart. Hydrogen and oxygen escape and burn, creating the enormous fireball seen on television. And the shuttle is torn apart by the forces of the air around it. All 7 people on board are lost. Francis Scobie, Michael Smith, Judith Resnick, Alison Onizuka, Ronald McNair, Gregory Jarvis, and the teacher Krista McAuliffe. After the accident, the United States creates the Rogers Commission to investigate what happened. One member of the commission is a physicist named Richard Feynman. And during a public hearing, Feynman does something brilliant. He doesn't give everyone a long, complicated lecture about rubber. He takes a small piece of O-ring material, he squeezes it with a clamp and places it in a glass of ice water. Then, after the rubber becomes cold, he removes the pressure, and the rubber stays compressed. It doesn't immediately return to its original shape. That's it. In just a few seconds, using a glass of ice water, he shows the basic problem on live television. The cold rubber is slow. And for a seal that has to move in a fraction of a second, slow means failure. But here's the thing. The commission discovered that this wasn't only the failure of one rubber ring. NASA and Thiokol had already seen damage to these seals on earlier flights. They knew the booster joint had problems, but because the previous missions survived, the risk slowly became accepted. Richard Feynman compared it to playing Russian roulette. You can pull the trigger once and survive. Maybe you survive several times, but every time you survive, the gun doesn't magically become safer. You were just lucky. And you know, there wasn't one evil person sitting in a room who knew everything and decided to destroy Challenger. The truth is more uncomfortable than that. Some engineers understood the cold. Other people knew about the damaged O-rings. Managers knew the mission had already faced delays, but nobody making the final decision received the complete picture. As the warning traveled through meetings, telephone calls, and management levels, it became weaker. A serious engineering concern slowly turned into something that looked like an acceptable risk. The machine failed at one joint, but the organization around the machine had been failing for much longer. And that, honestly, is the part of the story that stays with me. Challenger didn't fail because absolutely nobody saw the danger. People did see it, but the right information didn't reach the right people with enough force to stop the launch. Every previous successful flight had made the problem feel a little less frightening. But success doesn't always prove that the system is safe. Sometimes it only proves that the system has been lucky so far. 7 people trusted that every warning had been heard. It hadn't. A small rubber seal opened the path to the disaster. But weak communication, incomplete information, and warning signs that had become normal allowed the launch to happen. And 73 seconds later, the whole world saw the result. If you enjoy simple stories about complicated failures, you can subscribe to Failure Atlas. And let me know in the comments which disaster or engineering failure we should explore next.